Good afternoon. So, now today is our lecture 17 in our series, and we will continue our discussion of convolutional codes. Let me just get started with, so this will then be lecture 17, the Viterbi Decoder. And perhaps we should just recap our last lecture here, and let me zoom out and increase the zoom a little bit. So, in the last lecture we were concentrating on the state and trellis. While discussing convolutional codes, we are looking at various representations of the code, and a very useful representation is that of a trellis, and the origins of the trellis lie in the state diagram. So, that was the theme of the last lecture. We started out by first completing our earlier discussion on formal power series and polynomials, and if you will recall, we had given a polynomial description for the encoder here. So, if you look here, you will see that what we have on the left is a polynomial description. Let me just make sure that I can see two pages here. So, on the left what we have is a polynomial description of an encoder, and this is we called our polynomial generator matrix, and the input output relationship is in terms of power series. So, there is a power series that represents the input, and there are two power series that represent the output, because in this case the convolutional code has one input and two outputs. And then we drew the finite state machine diagram for the convolutional code, which directly relates to this state diagram that you actually see over here. We looked at the finite state machine, and this is the table that tells you that if you are in a given state and you have a given input, what is the output, and we have labeled the diagram according to that. We started drawing the trellis just to give the idea, and here is the completed trellis, and I actually have two versions of the trellis. One version I have kept, the idea being that I wanted an unlabeled version, and then here is a labeled version which has the output. So, let me just make this a truly unlabeled version by removing these the labels on top here. Okay, good. So, we have an unlabeled version, and then we have a labeled version, and we are going to actually use both. So, let me the way we will actually begin today is by copying, we will begin by copying this particular page. I am going to select the page, then we will copy it, and let us paste it in our new note. Okay, so it is now pasted, and so I will write a very quick recap here. So, the recap is that we completed our discussion on formal power series, and polynomials leading to the polynomial generator matrix of the convolutional code. Then we went on to talk about the state diagram of the encoder viewed as a finite state machine, and then we started drawing the trellis. Diagram. And as I think I mentioned last time, the trellis is nothing but an unfolded state diagram. Basically, you are making a distinction between the same state at time t and at time t plus 1. So, you keep track of time and states in this diagram, otherwise the connections are the same. And in this graph there is some terminology that is associated with this. For instance, so let me do one thing here, just to introduce terminology. Let me just pick out just the trellis, if I could. Okay. Copy the trellis over. Here I have the trellis. I am going to move it so that I have space to provide labels. And now what I am going to do, okay, there is a missing state here, let us put that in. So, one terminology is that of nodes. So, every one of these is a node. So, let me use a different color for this. So, these are nodes. Okay, so, these are nodes in the diagram, and what you see vertically across time here, these are node levels. So, this is node level 0, 1, 2, 3, 4, 5, 6, 7, 8, and these corresponds to different instants of time. So, this is node level 0, 1, 2, 3, 4, 5, 6, 7 and 8. So, these are the different node levels. Then now so this is a graph. So, these are nodes, it is very natural, and between two nodes you have an edge. We will sometimes also refer to an edge as a branch. So, we will call this either an edge or a branch. Sometimes we may even speak of a link. And now another thing to keep in mind is that the way we have labeled this, the way we have colored the edges in this graph is that whenever the input is a 0, we have an indigo color label, colored line, and whenever the input is a 1, it is red. And I also pointed out that, so that means that if I feed the encoder a particular information sequence, for instance, if I feed the encoder the all 0 sequence, then I will trace out, then I will be tracing out this particular path in the trellis. On the other hand, if I feed the trellis the all 1 sequence, message sequence, then I will actually be tracing this particular path in the trellis. Okay. So, in this way, and supposing it is alternating zeros and ones, so that is 0, that is 1, that is 0, that is 1, that is 0, that is 1, that is 0, that is 1. Okay. Sorry, there is no 1 here because there is no option for a 1 at the end. Yeah, but you get the idea. So, that means that for every, because in this trellis we forcibly forced the last two symbols to be 0. Okay. So, that was the reason why I could not get to a 1. But in general you get the idea that there is a one-to-one correspondence between message sequences and paths in the trellis. So, in this way you now you understand that I can associate with a path a message sequence, but at the same time I can also associate with every path a code word, because in this trellis I have also labeled the branches of the trellis with the output of the convolutional encoder, and in this way I can actually associate with every path in the trellis a code word as well. So, let me just go back to this labeling that I had here. Let me just fill in. I erase this, so that 0 0 0 0 okay. So, now I have all my branches labeled with outputs as well, and again repeating the same argument, but this time with a focus on the output sequence. You will see that if the input message sequence is all 0, the output message sequence is all 0 as well. If the input message sequence is all 1, which means you follow all ones except the last two being zeros, then the corresponding output sequence you can read off on the trellis. So, this is 1 1 0 1 1 0 1 0 1 0 1 0 0 1 and then 1 1. Okay. So, in this way every path with the trellis is connected with both a message sequence as well as a code word. Okay. And a path is basically a sequence of edges or a sequence of branches or a sequence of links. Okay. They are all the same thing. Okay. So, we have got that terminology out of the way. Now, what we would like to do, so I have entitled this lecture the Viterbi decoder. So, our focus now is on using this trellis to actually decode the code when you have sent a certain message across the channel and at the other end of the channel you have received a certain received sequence, and now what you are interested in doing is trying to find and recover the underlying message sequence. So, we have to make a choice there. So, I think by now, so let us see how I want to do this. I think that I am going to copy that trellis one more time. Okay, so let us try that once more. Okay. So, I have selected perhaps a little more than the trellis, but that is okay. We will paste it here. Okay. Now, let us get rid of some of the unwanted lines. Okay, good. So, let us say now that here in a particular instance where I want to illustrate how decoding works now. So, let us assume let me see if I can actually scale the trellis down a little bit, then maybe it is not required, that is fine. So, let us just scale this, yeah, I think that would do it. Okay. So, I want to put down a particular input sequence here. So, let us say that the input sequence, and maybe I want to use let me use green for the input sequence. So, let us say that my sequence UK is 1 0 1 1 1 0 0 0. Now, the last two zeros are forced because we want to bring the trellis back to the all 0 state, and the reason for that, it's purely a convenience factor. In practice you don't need to do it, you can actually build a code and not have to terminate the trellis, because it turns out that there is a certain loss, small loss in information rate when you terminate it. On the plus side, you do gain a little bit in performance, but the biggest reason for doing that is that just for convenience in exposition, it is much easier to explain the convolutional code when you actually terminate it. So, we will assume that it has been terminated by putting these last two zeros over here trailing or terminating zeros. So, this is the message that you actually want to convey. Now, what path are you tracing along the trellis? So, you are tracing, since you are going 1 0 1 1 1 1 0 1 1 1, and then you have 3 zeros 0 0 and 0. So, that is the path that you are actually tracing out on the code. So, let me see what I want to do. I think the wise thing for me to do right now is to make several copies of this trellis, because I want to represent different things on different versions of the trellis. So, let us do that. Let us select the trellis and copy it a few times over. Okay, good. So, I have got the trellis copied a few times. Yes, I think I have the trellis 1, 2, 3, 4, and we are working on this one. Good. Now, so then what I want to do is I just want to illustrate the input sequence here by putting this rather dark, no, that is too dark. Let us see, how do we want to do it? Maybe I will try to put an arrow along the path. So, let us put, this was 1, this was the 0, this was the 1, 1. So, that is 2 1s, 3 1s, and now 3 zeros. So, if you follow the arrows, so let me zoom that a little bit. So, if you follow the arrows now, so you have 1 0 1 1 1 0 0 0, you actually have the message sequence. But more than that, you also have the corresponding output sequence, which is given by, again let me use green here. So, that will be V 1 K, V 2 K. So, I have my output sequence here, and I want to focus only on the particular message sequence that I have identified here. So, the corresponding output will be therefore the output that corresponds to this. So, I think I am going to have to zoom out for that to write that. So, if you look at the top sequence and then look at the path, then you will see that the output is, here I have a 1 1 1 0 0 0 0 1 0 1 0 0 1 1 1 1 1. The last is a 0 0. The last is a 0 0. Let me just check that it agrees with what I have in my notes. Yes, it does. Okay. So, this message sequence on top is associated with this code sequence here. Now, I want to deliberately introduce 2 errors. I am going to deliberately introduce 2 errors and then show you how we will actually decode. Now, it turns out that this convolutional code can correct, well, the error correction capability of the code depends on where the errors occur. Since we are only dealing with a small segment of the code, it is wise not to introduce too many errors. So, let me introduce 2 errors. Okay. So, normally if this was a classroom setting, I would ask someone in the class to pick 2 of the symbols to raise, but since we can't do that, let me do the picking. and now I am just going to arbitrarily correct 2 of these. So, then that will be R k 1 R k 2, these are the 2, and I am going to change, I will put a small arrow to indicate the ones that I am going to change. I am going to change this symbol, and I am also going to change this symbol. It does not really matter, I have to pick something. So, now the received sequence therefore, because of the errors will be 1 1 1 0 1 0 0 0 1 0 0 1 1 1 0 0. And so, now the question is, how would you actually decode the code? So, for decoding, what you want to do, and this is the brute force way of decoding the code. So, if you will recall, when we talked about decoding a block code, we said that to decode a binary block code, if you were interested in minimizing the probability of code word error, what you would have to do is do maximum likelihood decoding. And if the channel was a binary symmetric channel, then that maximum likelihood decoder, and if all the code words are equally likely, which is almost always the case, then you would choose the minimum Hamming distance decoder. So, here that is the goal. We want to use the trellis, and given a particular received sequence, what we want to do is we want to identify the code word that is closest in Hamming distance to the particular received vector. So, that is our goal now. So, and the way we the easiest way to do that, to see that on the trellis, is to actually go into every branch and write the Hamming distance between the output associated with the branch and the true output of the code word associated with the branch and the received distance. Okay. So, we can do that, and if we do that, then I think that so let me copy this page over, and we will reproduce that here. Okay, good. I also want to select okay, so let us see what happened here. Okay. Let me try that one more time. I want to copy this page here, this entire page, select page, and now new page and paste. Okay. Okay, so it appears that that is a little tricky and time consuming, so let us not do that. So, let me just paste the received sequence separately. Okay, so we have that here. So, in fact, let us move that a little bit closer to the trellis. Okay, here we go. And now what I want to do is, I want on the trellis, I want to mark, I want to focus on the received sequence. So, I want to focus on this and mark on the trellis in place of the output sequence. I want to mark the Hamming distance between the corresponding received segment and the code word. So, I guess I can delete this. The actual code word is not of interest now. We are decoding. So, like the receiver, the only thing that we have access to is the received vector. So, now we will go ahead and put the branch, what are called the branch metrics, which are nothing but the Hamming distances. So, focus on this branch over here. The output is 0 0, but the received vector is 1 1, which means that the Hamming distance between the output associated with this branch and the received vector is 2. So, likewise on this branch it is 0 0, this is 1 0, the Hamming distance is 1. So, these distances are called branch metrics. Okay. So, let us put down for every branch in this trellis the corresponding branch matrix, and I feel that the easiest way to do it is to actually go by fix a certain branch where you know the output, and then look at the corresponding received signal and then compute the Hamming distance. Okay. So, for that let me do that in red. So, the branch distance here is 2, 1, 1, 0. Okay. So, I am just a little bit worried about missing the alignment. So, let me just adjust this a little bit. I think this needs to be shifted just a little bit to the right. So, let us move this to the right. Good. And then perhaps I will actually draw certain lines which help demarcate this. So, here is this. So, for every section of the trellis I am going to use the corresponding output. So, that makes it more clear. So, right now I am operating here. So, the branch metric here is 1. Is 1, this is 1, that is 2, and that is 0. Okay. So, now that we have written down those branch metrics, we can actually get rid of these symbols. Okay. And similarly, we can do that with the other branches. So, let me do that with these branches here. So, the branch metric here, because it is the distance between the all one branch that is coming down and what is in here. So, that is 0, 1, 1, 2, 1, 1. Okay. And let us delete these 1 1 symbols. Okay. Then the next is let us focus now on the branches that are going up, where the output again is 1 1. So, we have 1 2 3 4 5 of these branches which pick up metrics starting from the third. So, let us do that. So, this one would then be 1, this would be 2, this would be 1, 1 and 0. Sorry, that 0 is for a different branch. We are only interested in the branch, that is correct. That is correct. So, that was a 0. Okay. Let us remove the corresponding entries. Okay. So, this is a little bit tricky given that it's okay. So, let us continue that. So, hopefully, I have got it right. So, now we have done it for the 1, 2, 3 classes of branches. So, there are 5 more to go. Let me take care of these 4 at the bottom where the output is 1 0, but looking at the true output, we see that the Hamming distance is 0, 1, 0 and 2. Then we have these downward branches here where the output is 0 1. So, let us put down the metric for those branches, and their output is 0 1. So, the metric is 2 here, this is again 2, this is 1, this is 2, and this is 0. Now, take a look at these branches here which have labeled with 0 1, 1 2 3 4 5 of them, and let us put the branch metric. This is the third segment 0 1, but it is actually 1 0. So, that is Hamming distance is 2. So, 2, here the Hamming distance is 1, that is 1, S 2, 0, okay. So, yeah, hopefully we will be able to handle this. It is getting a little bit crowded in here, but I guess the good news is we have only 3 more branches to go. So, here is a branch which is 1 0, 1 0, 1 0, 1 0, 1 0, 1 2 3 4 5 6 instances of it. So, let us take care of that. So, here so that was 0, and here again it was 0. This one was 1, this one was 0, this one is 2. Alright, so now okay, there is this one branch which we must have forgotten. This is 1 0, so let us put down Hamming distance of 1 for that. We are only left with the 0 0 branches. These are the branches that are going 1 2 3 4. So the Hamming distances are 1 0 1 1. So that is 1 0 1 1. Okay, so I think we have actually done it. So now we have managed to there is one other yeah, I think here the issue was there is one output whose Hamming distance is 2, and here we did not get rid of these because I think the 1 and the 2 were running too close together. Let me see if I can fix that here. Okay, so we have got rid of that. So now you have labeled the entire trellis with the branch matrix, and decoding now is just a matter of actually going along the paths and seeing which path has the least metric. The brute force method would just look at all the paths in the trellis and then say what is the metric of each of these, and the metric of a path is the sum of the metrics along its branches, because after all you are computing Hamming distance between a code word and the received vector. So you can just add the metrics along the branches. Now that would involve computing the metric of every code word, which is too many code words, and you do not want to do that. The key and aspect of the Viterbi decoder is simply that you can actually discard some paths as you go along, and we will illustrate. So here we will go node level by node level. So at this node level you actually see that you have there are two paths, one which has a branch metric of 2 and one which has a branch metric of 0. So at this point it looks like this may have been the more likely path taken by the code word. Okay. So if you like, you can actually put let us choose a different color to indicate branch metric, and maybe what should I choose? Let us see if yellow stands out. I guess it does not. Maybe I should use black. How about black? So this one is 2 and this one is 0. Now I am attaching the branch metric to the nodes, just so that I know that the path leading to this node has higher Hamming distance than the path leading to this node. We come over here. Now 2 plus 1 is 3, so I will put down 3 here. 2 plus 1 is 3, 0 plus 0 is 0, and 0 plus 2 is 2. So at this level you see that the node metrics are 3, 3, 0, 0, 0 and 2, which means that the path leading to that node from the start node, okay, this is our start node, so the path leading from here, from the start node to this node, has metric 3, here it is 3, here it is 0, and here it is 2. We keep going. So now it is here it is 4, and here it is 4 and 1 and 3 and 3. Okay. So now we see there is something interesting though that happens here. You say, wait a minute, I can't quite do that, because in reality to each node now I have 2, to each node now I really have 2 incoming paths. So which do I choose? So I have to make a choice. So the answer is, as you might expect, you choose the more likely path, and this is where the rejection that I was telling you about comes into play. So, now there are two paths that lead into this node, one which has a metric of 3 plus 1 which is 4, and the other which has 0 plus 1 which is actually 1. So, we will take the lesser of the two which happens to be 1. So, we will attach that to this node. So, this is 1, and let us just put an arrow up here to indicate that we have made this selection. Okay. Now, at this metric, the branch metric here is 3 plus 1 which is 4 or 0 plus 1 which is 1. So, we will put down the lesser of the two which is 1 and we will indicate that it came from here. Now, down here it is either 3 plus 0 or 2 plus 2. So, the 3 plus 3 0 wins and we will indicate that, and here it is 3 plus 2 or 2 plus 0. So, the 2 plus 0 wins. So, we will actually put down that here and we will put an arrow here. So, that means, and then just to be consistent, let us also put an arrow in the previous paths, because although there was no selection to be made there, that was only because there was only one incoming edge to each of the nodes. So, now at each node, if you trace back along the path, you see that you see the path that is most likely, given what you have seen thus far, to be the code word in terms of Hamming distance. Okay. So, that these three, so in a way decoding is about picking the winner, and the winner is the code word that is closest in Hamming distance to the received vector. What the Viterbi algorithm allows you to do is it allows you to identify losers, that is code words which can never be closest, and throw them away. So, we did that the first time we actually did that was at this node, because here we had a choice between this and a choice between this, and since in this case this won out, this means that this lost. What does that mean? Because after all, this is only a part of a code word. It means that any code word which begins in this manner and continues with however it continues will always lose out to a path of this type, because no matter what you can add as a suffix to this path, you can also add it to this. So, if this path has lost to this path as this node, it is lost forever, because beyond that whatever happens is common to both of them, and therefore, it cannot change the situation. So, the relative comparison remains, and so you have a loser here, in that sense that can never be the closest code word. So, what remains are called the survivors. So, at each node you have a survivor, and the survivor metrics are 1, 1, 3 and 2, and you also attach them to the node, but really they are the metrics of these survivors. Let us continue here. At the next node level, you have a choice between 1 plus 0 or 3 plus 2. So, 1 plus 0 wins, and now you have a survivor. You have rejected this path. 1 plus 2 or 3 plus 0, that is a tie. Now, in case of ties, you just arbitrarily flip a coin. Let us say that I prefer to take the downward arrow always. So, it is 1 plus 2 and I will put down 3, and here it is 1 plus 1 or 2 plus 1. So, that is 1 plus 1, I select this, and here it is 1 plus 1 or 2 plus 1. So, I prefer the 1 plus 1. So, I pick this. So, again at this level I have 4 survivors, and by tracing back I can identify, for instance, if I am here, the survivor at that is this particular code word. If I am here, it is this particular code word, and so on. Now, let us go over to the next and continue this. So, here it is 1 plus 1 or 2 plus 1. So, that is 2 and we pick this. This is 1 plus 1 or 2 plus 1. So, that is 2 and we pick this. This is either 3 plus 0 or 2 plus 2. So, that is 3, we pick this, and here it is either 3 plus 2 or 2 plus 0. So, we pick the 2, we pick this. Again we have 4 survivors, and this keeps on going. So, it keeps on going till the end, and we will see what happens there. So, now continuing here, it is either 2 plus 1 or 3 plus 1. So, that is 3, we pick this. This is either 2 plus 1 or 3 plus 1, 4. So, that is 3, we pick this. It is either 2 plus 2 or 2 plus 0. So, that is this, and we pick this. and here it is either 2 plus 0 or 2 plus 2. So, that is 2, we pick this. Over here it is either 3 plus 2 or 2 plus 0. So, it is 2 plus 0, we pick this. This is either 3 plus 1, 4 or 2 plus what was it, 2 plus 1, this is supposed to be a 1. Okay, so, it is either 3 plus 1 or 2 plus 1. So, that is 3 plus 1 and we pick this. So, now it is either 2 plus 0 or 3 plus 2. So, the 2 plus 0 picks and your metric is 2. So, that means the path that is closest to the received vector is Hamming distance 2, and now we are finished because you can trace back. So, let me now copy this page again, select page, copy page, insert page and paste page. Okay, good. So, what that means here is that now let me use this thick brush here to identify what exactly we have decoded. We have decoded this path, this one, because we are following back from here. So, because this survivor won out, so that is 1, that is 2, that is 3, sorry. So, we want to trace back along the arrows. So, that is 3, that is 4, that is 5, that is 6 and that is 7. So, we are actually saying that the winning path went like this, and from that we can actually read off the underlying message sequence, and let us see if we can do that. So, that underlying message sequence will then be a 1, a 0, a 1, a 1, a 1 and then a 0, 0, 0. So, it is 1 0, 3 1s, 3 zeros. And if you go back and look here, you will find that it is hopefully the same, 1 0, 3 1s and 3 zeros. Okay. So, we were able to decode the code, and that is not surprising if you know a little bit more about the properties of the code. Anytime you create 2 errors, you are always going to be able to decode. In actual fact, you can actually decode more. You can decode a larger number of errors, but then you have to worry about where you place the errors. Okay. So, that is how Viterbi decoding proceeds. So, maybe I should just put down a few notes correspond to some of the terminology I introduced here. If Vk1, Vk2, k goes from 0 to m minus 1, where m is less than or equal to n, is the output of the convolutional encoder then the associated metric then the associated path segment metric is given by the Hamming weight between and the corresponding received sequence. Similarly, an edge or branch in the trellis associated to code symbols is the Hamming distance of then so that these are just some notes to accompany our discussion of the decoding. In the Viterbi decoding process, with each node at each node level we associate a survivor where by survivor we mean the path from the start node so I should just qualify this and say whereby survivor at a node. So let me do this. Whereby survivor at a node we mean the path from the start node to that node having least path metric. And in brackets I should add, we also store the survivor itself. So, in closing, yes, this so I guess the technology has its limitations. If we had a board, sometimes describing the encoding, the decoding process would go a little bit faster. So, with this technology it is a little bit slower, but I guess on the other hand, the flip side, there are some things which are faster using technology. So, I think it will all even out. So, today we basically discussed the Viterbi decoding algorithm, and I actually carried through an example using our example trellis, and I showed you how the Viterbi decoder reduces complexity by being able to identify, in some sense, if you think of decoding as choosing the winning path, it allows you to identify losers early enough so that you do not spend a lot of time with the losing paths and are able to quickly identify the winning or the code word that is closest to the received vector. So, next time we will continue our discussion on convolutional codes. Thank you.